Hi, my name is Peter Holmqvist, and I will present some work we've done here in collaboration with Kim Kristiansen and Signe Kjellstrup here at PoreLab in NTNU, Norway. So I'll talk about the Seebeck effect in membrane systems of ions abundant in seawater and how that can be used to increase the electricity production in reverse electrodialysis. So first, what is reverse electrodialysis, or RED? Well, that's a technology to produce electricity from salinity gradients, for example, from seawater and brackish water. This is done by using ion exchange membranes to let the ions pass through. So cations permeate through the cation exchange membrane and anions permeate through the anion exchange membrane. This creates a net electric current which can be harvested through an external circuit. Typically, for one such unit cell run on seawater and brackish water, the concentration potential is 150 millivolts. However, if we heat one of the streams, if we heat the brackish water stream, we can get an additional thermoelectric potential by utilizing the temperature difference across the membranes. We have previously measured this effect to be 1.9 millivolts per Kelvin for an RED unit cell. However, we don't know the effect of the different ions because we used natural feed waters in this unit cell. So, mathematically, this potential is expressed through this equation. The electromotive force has contributions from the temperature difference, where this is the Seebeck coefficient. And we have also contributions from the concentration potential, where this is the chemical potential gradient of the water and the salt evaluated at the temperature on the left-hand side. So there has been done some studies on this already, on the effect of the thermal gradients in RED. What has been shown there is that the increased temperature lowers the cell resistance. However, in work done by Benneker and others, have shown that RED with currents in the ohmic regime, there was no significant effects from the direction of the temperature gradient, which implies that the thermoelectric potential in this case was negligible. This is interesting, and one reason for this could be that there was large heat transfer between the streams and reducing the effect of the thermoelectric potential. Another could be differences in the ion exchange membranes. However, we are interested in learning more about this Seebeck effect, and that is what we will go to now. So, what we have done is measuring the Seebeck effect and only the Seebeck effect. So we have not had any concentration gradients in our system. This allows us to only measure the effect due to the temperature difference across the membrane. And we have done so using FUMACEP FKS cation exchange membranes. And we have studied a sample of natural feed water and single salt solutions of the most abundant ions in seawater. So we have used solutions of sodium chloride, potassium, magnesium, and calcium chloride. And we have also looked at binary solutions of sodium and magnesium chloride. In this last binary solution experiments, we have also developed a method to estimate the transport numbers, which gives an indication of how the different ions contribute to the Seebeck effect. So, for the seawater, we used a sample from the Trondheim fjord. It was quite a low salinity sample, so the salinity here is about half the oceanic average. But we measured the Seebeck, the membrane contribution to the Seebeck effect to be 1.2 millivolts per Kelvin. And this is interesting because that is actually higher than what we would expect in a pure sodium chloride solution, which implies that the effect of the other ions play an important role. However, these effects are still unknown, and is what we're going to look at now. So the first step on that way is to investigate single salt solutions of the different ions. So we have looked at the single salt solutions of the most abundant cations in seawater. And what we can note immediately is that the Seebeck coefficient is in general higher for the monovalent ions than the divalent ions, and that it decreases linearly with the electrolytes or the logarithm of the electrolyte activity. This is expected as we can see from the expression for the Seebeck coefficient. We have the three last terms there being approximately constant at in our concentration range, while this first term is the partial molar electrolyte entropy, which varies linearly with the concentration or the activity. So this gives us a method to measure or to estimate the transport numbers of the ions, which is shown here. But for a more in-depth analysis of the different ions, we have manipulated the expression a bit. So we have subtracted the concentration-dependent term in the expression from the membrane contribution of the Seebeck coefficient. That leaves us with a term which is constant for the different concentrations, and we have called this term the lambda. So what is interesting about the lambda is that it shows a linear correlation with the cube of the hydrated radius. And while we not yet know the nature of this correlation, it could be useful to estimate the performance of other ions. And we will also use this lambda value for the next section, which is the binary solutions. So to understand the Seebeck coefficient in binary solutions, it is useful to know the contribution from the different ions, and an important parameter here is then the transport number of the magnesium. So what you have done is that we have looked at systems with only sodium chloride and then added a small amount of magnesium chloride and looked at the difference between these two systems. So by using different concentrations of sodium and then the same ratio of magnesium and sodium, let us formulate these equations. So for the binary system, the Seebeck coefficient takes this form. And the first term here is the sodium contribution, and then we have the contribution from magnesium, and then the contribution from chloride and water. If we now take the difference between the pure sodium chloride system and the binary system, we can formulate the difference as this. And what we can see here is that this term is, or this expression is known, it's the activities of the magnesium and sodium chloride. And then we have this term, which is also constant and known, where we also used these lambda values from the previous slide. This leaves us with only one unknown, and that's the transport number of magnesium. So this lets us estimate the magnesium transport number. So what we have done is that we have looked at systems where we have added 2%, where the concentration of magnesium is 2% of the sodium concentration and 3% of the sodium concentration. And what we can see here is that the effect is large compared with the pure sodium chloride system, which is the black points. So even small amounts, 2 and 3%, gives a large effect, a large negative effect on the membrane contribution to the Seebeck effect. And this can be attributed to a high transport number of magnesium in the systems. So the transport numbers are 0.5 and 0.7 with the standard or double standard deviation of 0.4 and 0.5. You can note that this high uncertainty is both due to the low concentrations we have used and that error is propagated from the estimated lambda values. So the larger span of concentrations and more refined lambda values, this uncertainty could probably be lowered significantly. But it shows a method to estimate the effect of magnesium. And again, this high magnesium transport number can be attributed to a high fraction of magnesium in the membrane, and shows then that even if there are small amounts of ions in the external solution, they can play a huge role in the membrane. So, to conclude, we have shown a method to determine the membrane transport numbers in binary solutions, and where we have found that for 2% of magnesium, the transport number was 0.5 plus minus 0.4, and for 3% magnesium, we found the transport number of 0.7 plus minus 0.5. And in single salt solutions, we have measured the membrane contribution to the Seebeck effect in sodium, potassium, magnesium, and calcium chloride solutions, and also found a relation with the hydrated radius of the ions. For the binary sodium magnesium chloride solution, we saw that even small amounts of magnesium led to a large decrease in the Seebeck coefficient. And while this cannot explain the high Seebeck coefficient we saw in seawater, it highlights the effect that even small amounts of ions can have when having a mixed electrolyte. So work should be done on looking at how the other ions present in seawater can affect the Seebeck coefficient. Okay, thank you, and I'll be happy to answer questions in the Q&A session.